Hello and welcome. I'm Bill Wake. We're here working on a basic interpreter, an interpreter for the old basic language, and we made a lot of progress over the last couple of days. First, we got remark working, which is a do-nothing command, if you want to call it a command at all. It's the comment in BASIC, and we got that working end to end yesterday, not just the tokens. And then at the end of the day yesterday, we added a simple print, and this print, if you just have print by itself, we'll just have it put out a new line. And that went in pretty quickly. I mean, like in less than half an hour. Today's will not be a half an hour deal. What we want to do is start printing numbers, and we should print numbers and strings. The thing with this is the numbers you print, they could be arbitrary formulas. So I don't think we'll finish arbitrary formulas today, but we'll make a dent. Okay, let's see where we are. We've done what we've done so far has been all through the test system. So let's pull up a sample test, I guess. Okay, here's a very simple test. 20 print. We interpret that program and run it, and the output we get is a new line. Okay, that's as simple as it comes. Well, maybe not. Here's 10 rem comment. The output is nothing. Okay, so you can tell we're not too far down our journey yet. We do have a number of tokens, one for the end of file or end of input, errors, the line number at the start. We got a little work to do there. Remark itself and print. So each command is getting its own token. And the idea is, and this is sort of well-established compiler structure kind of thing, just over literally hundreds of compilers, this sort of design emerged that often it's easy to just do lexical analysis first, identify the tokens, and let that worry about spaces and new lines and finding, connecting to files and all that stuff. And then once you have tokens, then define a grammar and do a parsing of it, and you're parsing the tokens, not the characters. So you're dealing with a little less stuff and a little more structured. So you can see our error message has a string and our line number has an integer. Other things will have data attached. So when we get to names, those will have their string attached as well. So you can define your grammar in terms of names and not have to worry about, are you talking about A0 or B9, Okay. The other thing that we ran into, and I never quite managed this part right on the these high-level tabs and lower-level tabs and Xcode, I just don't get it. We'll cross this one out in a moment. But one thing we ran across was this question of error handling. So let me see if I can explain what we're doing there. Let's go to the parser. All right. Now I'm going to go back to do. So in the parsing, I mentioned grammar before. This is the way we can define these. So I do a mix of sort of various grammar formatting kind of things, but sort of mixed with regular expressions. But on the left side are the non-terminals, at least the way we're working. And on the right side are terminals or non-terminals. Terminals are the tokens we have, and non-terminals are other grammar rules. Okay, and so we say a program consists of 0 or more lines. Each line has a line number and a statement and a new line. A line number is just an integer. A statement can be rem to the end of the line or print. Okay, so pretty minimal grammar at this point, but there's room for things to go wrong, of course. And when you translate this, I'm using recursive descent, which says basically, if your grammar is structured the right way, which I will make sure ours is, you can treat each non-terminal as turn it into a method, and then the method consists of finding the stuff that's in the right-hand side. So if you remember, program went to 0 or more lines. Well, here I'm calling the line method, and I'm appending all those lines together so I can build a tree out of it. But the big thing is, line takes care of each line. Okay, and so if the token is line, then we have the number at the front of things, And given that, we can go ahead and parse the statement. And the statement looks for, at this point, remark or print, and otherwise there's an error. Okay. So the challenge is when there's an error, we always return a parse, which is a tree. We'll go look at that thing in a minute, but parse is a tree, and we're just shoving error nodes back. Okay. That's not a great way to do it, because now we have a tree. The top level has valid stuff, and the lower levels have junk. Okay. The lower levels have, they have errors in the middle of them. So I've got this expression tree with an error down there. Well, that knowing there's an error down there doesn't really do me much good. I want to bubble them up to the top more. So this is kind of this thing. And yeah, one of the things that separates sort of the toy projects from the production projects is error handling, and this primitive error handling we have that basically, if it ever tries to execute an error node, it'll blow up, so that's kind of bad. And we also need to, so I want to do something where these errors bubble up to a much higher level. And so the easy way to do that in Swift and Java and lots of other languages is to use try-catch and exceptions rather than returning nodes and pretending things didn't go wrong. Now you could make this returning node thing work, like if you were, kind of coalescing things and you check for errors and blend it back. I don't know. It's a compromise one way or the other. The other thing is you have this thing when there's an error, you're not quite sure what to do at that point. And so even this simple one, what if we left off the line number? Well, I don't know. There's not much we can do. Like, statements have to have line numbers. Okay. And so really, like, you may as well just skip forward to the end of the line and try again. Okay. And so we would like to be able to impose that kind of error handling or error synchronization on this thing. Okay. Another thing is we'd like to report things a little better. And, I'm going to do this in levels. The first level is what we have now is error nodes. The second level could be pull those errors up and track them somewhere. And the third level, I would say, like we ought to be keeping track of which line the error was on at least. Okay. An error message that says your program has a problem is not really very helpful. Okay. Now there are compilers out there that just find the first problem and stop. And, if it's interactive and fast, maybe that's okay. But it's much more common that compilers can accumulate all the errors and at least give you some sort of pointer to where they are. Now, ideally, we would put stuff in the line and maybe color it red and put an arrow and, explain it very carefully and all that. That's further levels. And I'm willing to get there at some point, but I don't want to start there. Okay, so the first test I want to do, or task I want to do, is improve our error handling. And I want to do that before we jump into the print, just because we're setting up a pattern for how you work, and I would like the parsing pattern to be good, okay, and effective, or whatever, how you want to say it. But I want to set up a good pattern for how we're going to work at least for a while. And also the other side of it is, odds are good I'm going to make some mistakes on the way, and if my message is totally buried and not anywhere, it's kind of a pain for me. Okay, so the deal is the parser normally returns a parse. Okay, now there's I don't know, not infinitely, well, maybe infinitely, but many methods, many ways to handle this. The one I'm thinking of is if our parser, or top level is our parser, if that could actually return the parse and the errors, that might be a way to go. it unfortunately bubbles things down. Another way to go is just to let the parser own a set of errors and let somebody come back and ask for them. Maybe that's easier. All right, let's try it that way, and then we may regret it. But having that list of errors, I don't know, maybe. Well, we can manage that list now, but it might be an input, might be a good thing. Then my screen interface can have, some sort of texty object that this appends to, and display it or whatever. It not, in the long run, I don't think I'm going to want to manage it here, but let's start there. Okay. All right, enough chatter. Let's see. So I'm just going to close this one. Okay, get a little more room. And let's see. Let me just squeeze this over a little bit too. Can I do that? No? Okay, never mind. Excuse me. Alrighty, so let's find our parser tests. No, I'm trying to keep the test on the left and the code on the right, but let's deal with it. Okay. So the approach I want to take for now, if there's an error, I'd like you to tell me your best description of it. And I'd like to leave that in some sort of error list of strings maybe for now, something like that. Okay. I'm not going to attempt to do positioning at all for now, although maybe that's worth doing. We'll see how fast, if I shut up and start typing, I guess. Okay, so the one thing I know for sure is in BASIC, like, it's line oriented. So if I go to the end of the line and try and start over on the next line, I've always got an escape. Okay. And the thing with error handling, and we saw this yesterday, if you joined then, if you mess it up and you don't consume any input, then you end up in an infinite loop, because the parser comes back in and says, okay, let's start looking at this token, and you've got the same error you're sitting on. You didn't advance the text. You get an infinite loop. So you got to make sure you're consuming stuff and making progress. And jumping forward to the next new line is definitely progress. Now, in our case, we don't really keep track of the new lines per se, but it's like the next line number. Now, that can screw you up if you had, if your line was 10 plus 20, okay, some sort of arithmetic expression, it may be that you just screwed up and, moving forward to the 20, and then it looks for the line, it may not be right at that point. Okay. And I would expect that if it's not right, we probably don't run it, but that's another day. Okay. So what I want to make examples of, basically the errors I have now. Okay. If I go into a line and I don't find a line number, I need to make an error message like this. Okay. And I need to be ready to handle it up here. Okay. So test no line number, rem remark. We just started like that. I want to assert, not the result. I want to assert that parser.errors is equal to well, I probably shouldn't have deleted that. Let's see. Let's just start here. Okay, this has no member yet that we haven't done that function, but it's going to have an array, and I guess I could probably put this all on one line. And I probably got one too many equals or parens. All right. If I had a parser.errors method and it produced this array, let's do it. Well, all right. I'm going to say var errors is an array of string and starts off empty. And I'm going to func errors returns array of string. I could probably do the get set thing, but I'm going to return errors. And I don't have to have the word return there. Okay. Oh. Let's call it error messages. Okay. This should fail. Yeah, we don't use the result. Yeah, so we're relying on that side effect. I think that's probably a legit complaint. Okay. The assertion should be empty is not no line number. Okay. So now I'm saying this method is going to be throwing. Okay, if I'm going to use try catch. And that should tell me, hey, you got to catch if you're going to do this. Okay. And is it... Let's do this. Can I... No. Is it catch? Catch something. All right. Yeah, it's do. Okay, yeah. I knew something was wrong with my head there. All right. And let's catch. Let's call can throw. Oh, yeah, we got to say try. Okay. All right. So what I'm doing is I'm assuring that, I mean, I have to say this line could throw, so you got to catch it. Okay. Now, I don't know if I want to create a little class. Can I throw a string? I can't remember. Let me get some. I think I may have to. Yeah, I can make my own, and maybe that's what I should do. Let's do that. And I'll just make the helper class up here, and we'll deal with it. All right, so I'm going to catch a parse error, and this is no line number. Maybe I should leave them enums. That might be okay. That might be a way to go. Let's get something going here, and then we'll deal with it. Okay. Throws may only occur before. Oh yeah. Okay. And if it's token, down here, I want to say throw. Throw. And we want this one, dot no line number. Let's do that. Okay. Expected expression. Cannot find no line number. Well, dot no line number. Type error. Do I really have to say parse error? Okay, so I'm throwing this parse error, no line number. I'm catching it up here. And again, let me make sure I'm doing that correctly. Do catch. I don't want anything. I want us to catch specific exceptions. I think I just put, like, yeah, name. Okay. Let's just do parse error. And there's a way to get the error. Where's that? It's if I catch, I should be able to say error messages dot append. I think it's just error. Okay, and then I've got to change the type of this to parse error. And then I got to change the type of this to parse error. Parse error dot no line number. Cannot convert. Okay. Am I back to compiling? No. Cannot convert error. Boy. I'm not doing the catch right. I know there's a way to do it. Because I just want to say, I want to catch any encryption error, and I don't think I can't say star. Okay, let's find another example. Really? Okay. This is weird. I mean, I really would like to restrict myself to any parse errors. No? Okay. We'll do this for now. All right. Undefined symbol, nominal type, whatever. Let's try it again. Hopefully that was just leftover. Oh, nope, there's something here. There we go. Okay. Oof. On the bright side, things should go easier for the next one. Okay. So a program, it still has this core piece of doing the lines, and I've made it so that the error handling I've made it so things do something no matter what. No, maybe that's not necessary. I mean, we're trying to continue parsing as long as we can, so I think it's okay that we're doing it this way. See, I have lines empty, and if something goes wrong on this big giant block of 8 lines, I'm gonna at least have my empty one, and I'm never gonna have an error thing in there. It's just the empty one. Okay. Let's take the next one. Unknown statement. Okay, so down here, it's really the only other one we have. Yeah, unknown statement. Yeah, I mean that's kind of correct. If it were, I mean, a statement wants one of our keywords. The keywords, it's all these, go to, data, def, and so on. If you don't have one of those words, you're messed up. It's not a valid statement start. Even if you just did 3 plus 2, that's just not a valid statement. You could probably do some sort of assignment. That's the one that doesn't have to start with a reserved word, but we're not handling that yet. Okay, so the parse error, unknown statement. Well, let's create one up here. Okay, and I don't know. My temptation is to put line numbers in already, but let's not do that. Okay, so this one is gonna. Let's see. The result. We're gonna do the same thing. We're gonna do this. Ignore the parse. Look at the parser.errors. And the result of this thing should be unknown statement. And that's parse error dot unknown statement. Okay, and that's one too many of these, I think. All right. So we have 42 remark, and we attempt to parse it. We come back, we've got an error, unknown statement, and that's what exists there. This should fail because we haven't dealt with it. Okay. And it's coming back empty. All right. We got no line number. All right, we just have to do the same thing. I don't know. I try and not say just too much, but it really isn't too hard here. We're just going to throw parse error dot unknown statement. Okay, and that's going to bubble up, but now this thing throws, we have to say try. Okay, and I think, okay, yeah. All right. And notice it doesn't have to catch it because that's just going to bubble up to the top. Okay, so we're just letting it go. Okay, so we're consuming the next token and letting it go. All right, and this should pass. Yay. All right. So we've made one small step towards better error handling. Let's find our to-do. Okay, error handling with try catch. Yes, we've done that. I guess I should do these backwards order, or I'll be wandering around for days trying to find them. Okay. And then I'm not saying we have to do it next, and I'm not sure when we'll do it, but let's add the next phase, which I would like to at least track line number of error messages. Okay. Now, I don't know if I want to, do I want to put it, I don't think I need to put it in here. But we could add an argument to each one of these to track the line number. But I think what we'll do is we'll grow the error handling stuff here. Currently you just append the message. We could do that synchronization forward and keep reading tokens until we get to a number or end a file, and then that would be our synchronization. So let's add error sync by skipping forward to next line number or end. Okay, so this will be you find an error in the middle of the line, skip forward until you hit the new line and the new line number, and say, okay, let's try again on this next line. Give up on that one. It's primitive, but usually you look at it and you go, oh, I see, fix it. Okay, alrighty. Certainly want to commit that. Error handling with try catch. Well, let's call it do catch, and maybe I'll learn it. Have it stick. The problem is I've used enough programming languages. I know there is a mechanism to do X, Y, Z, but the syntax of any particular language they're all getting blurred together. Okay. Now let's look at print with numbers. So we did a simple print. Okay, like this, 25 print. Now I would like to do a print. Let's print a number. Okay, traditionally 42. All right, we're gonna get several issues coming, so let's see how it goes. All right, so I print this. I don't expect my program. 25. That's fine, but parse.print. It's too primitive. Where's my parse? Let's open that thing up. So parse is the tree. Basically, it's the parse tree structure. And you see parses can contain parses, and it's an indirect class. So we can build up this tree-like structure. Okay, lines need statements, and programs consist of lines. I could be, I don't know if I could be more specific, but I'm going to trust that if I create well-formed trees, then I don't have to worry about the semantics that don't line up. So if I had programs and instead of putting in lines, I put in integers, like it's still a parse, but it wouldn't mean anything. We won't do that. Okay. You could define multiple types and all that. We might have to in the end define more types, but this will get us going for now. All right, but you see our print. So my line, oh, we don't use this anymore. Maybe we should take care of that before we go. There's a find usages. Well, selected text. Let's find selected symbol. Error, let message. Error here. Parse error. Well, I don't know why I got confused by that one, but let's get this one out. Now, that tells me interpreter probably has a test that checks errors. Or maybe it doesn't. No, it doesn't. Okay, so nobody's using this. This should complain. I'm sure it will eventually. Here we go. And we'll take this out. And run all tests. Okay, so here we are. We got program, we got line. We can look for particular things. Well, what I want is I can see print is going to have a series of stuff because the whole print statement. Let's go parser tests. The whole print statement is it can have 42 comma 3 plus x comma it could have a string ABC and a semicolon and another value 14. Okay, that would be a legitimate one. We're not going to start there, but you can have a series of expressions and separators, and these commas and semicolons have particular meanings. So a comma, uh, I'm not going to know the numbers, but basically a comma says tab to the next column after before you put the next value. So I think the columns were originally like 10 characters apart, maybe. So if you printed to column 15 and print 42, well, it goes to column 2, let's say, and you've got a comma there. Well, 3 plus x is not going to print in column 3 or 4. It's going to print in column 10, say, or 11. And semicolon, I think, says don't put any space after this. Okay, so it just it separates the values, but with no space between them. Okay, so we're going to have to deal with that. All right, but we're starting simple. We're starting down here. All right, now the next thing is, let's look at token. Okay, token, notice we have line int. Well, that int was the line number, okay? But that's not the same thing as the 42. Okay, so what I've done is by saying that was a line number, I kind of lied, I guess, or I didn't take into account what was coming forward, the fact that I could have regular old integers. There's also a problem around integer versus double, and for now, I'm going to ignore it. In OSI, basic OSI was an old computer brand. Commodore 64, if you heard of that, that was OSI produced them. Okay, so it used numbers kind of like JavaScript. It just has doubles or floats or whatever you want to call it, and some of those happen to be integers. Okay, I'm gonna let it distinguish integer versus double or floating point, and we'll blend that somewhere else and let that go. But I'm gonna first change this to integer. Okay. Can I just do a rename? Yes. Okay. And everything should work. Oh, so much for that. No? Okay. All right. And that's sort of a simple element. At some point I'll have to do double, and I'll have to decide if they're really the same. And if they are, then how do I make sure that line numbers are only integers and not doubles? I can't have 25.0, even though it's a legitimate double. It's not a legitimate line number. Excuse me. All right. So let's save that. Rename line to integer, and I guess that's a token. Line to token.integer. Okay, moving us forward on this thing. All right. Now, if I were trying to do anything more complicated than 42, we'd have to go back and do some work in our tokenizer, our lexer. Tokenizer, lexer, lexical analyzer, all kind of the same thing. But because we're not introducing any new tokens, I can skip that part, and I'm going to start right in the parsing. Okay. Now, this parse tree, I don't have anything that looks like an integer or an expression. Okay. And we need it. Okay. So let's make a number node. Well, how do we want to check? What we're checking is when you do a parse, does it come back with the right parse tree? Okay, so if you had this parse tree, what I'm saying is print is going to need a list of stuff, okay? Because now we're going to allow a series of items, okay? And I could just do one and grow it one piece at a time, but I'm going to say, hey, this is really a list of stuff. So let's define our tree more this way. So in effect, I'm making I'm kind of refactoring. I'm going to say, well, suppose we had made it an array anyway, and you always just had 0. Okay, so I'll add in this possibility that you have subtrees, and some things will break. Okay, it shouldn't even compile. All right, yeah. We have parse.print. All right, well, we need to return an empty list now. Okay, so just parse by itself. I'm not trying to be, I'm not, I say mindless, and I know it's not quite the right attitude. And so I try and say mechanical now. I'm going to mechanically solve this and just insert empty parens, empty brackets on every one of these. Did I leave one? Parse.print, what's your problem? Cannot type array of parse to print. I think that might be okay. What about this one? That's a real one. Okay, so I'm not doing any grand solution. I'm just trying to make it all come together. I think they just haven't caught up to that. So let's try again. Yeah. Okay. And parse as associated value to parse dot print. I don't know. That's a little bit of a let's try a better message. I try and write my messages so an end user could make sense of them. Sometimes I can't, and refactorings I don't necessarily bother, but this one, so let print have 0 or more expressions. Okay. So let's get back to our test. We're going to say 25 print 42. Well, the contents of this thing should be that parse tree, which is going to be the integer token. Ooh, so no, it's not. It's going to be, I'm going to need something for that. I guess I'm going to need a number. And I think it's going to contain a token, which is the number itself. Okay. So my parse.print, it should contain parse.number with a token, and the token should be token.integer with the value 42. Okay. Now I'm going to, let's see, I can do it this way. Try and spread this out a little so you can make sense of this. So a program consists of a line, which consists of a token, and a parse.print, which consists of a number which is the integer 42. Okay, now there's an alias thing. And you tell me if this is horrid, but we say token and parse so much. I think I can, is it type alias? Type alias. Let's try p equals parse. Okay, I gotta decide if this is worth it or not. But what I think I can do with this is p.program. Maybe I don't even need it. Do I need it? I never can tell when I have to specify the type of these things. Oh, if I don't need that, then I'm not gonna bother. Let's see. Let's just run the test. Switch must be exhaustive. Switch parse. Oh, okay. Case dot number. Let's just ignore it for now. Okay, I'm just gonna let that sit for a bit. Okay, parser tests. Okay, I'm okay with this style, and I think I can skip parse.skip. Let's find all the parse dots. Parse dot. Okay. And I just don't let myself do it everywhere. Just I want to see it go by. Okay. Yeah, these are much more readable to me. Just parse dot was overwhelming. Okay. All right, and let's try the same thing with token. It knows it should know in context which ones are there. Okay, we're in the process of this one. Okay. Forgive me the background noise. All right, let's get these other ones out of here. So I'm trusting that I know the difference between the tokens and the parse values. You know, the parse ones. I don't think it's confusing. I think it's actually kind of more readable. All right, and let's take the X off. Well, let's see. Yeah, that's okay. Run it with this, check it in, and then we'll take the X off. So remove unnecessary parse dot and token dot to make values more readable. All right, and back to our scheduled thing we're working on. Okay, so this one failed. Program token integer 2 parse print did not have our integer in it. Didn't have our number and our integer with the integer inside. Okay, and we can easily see why in our parser. Okay, so the parser, here's the print statement. It just looks at the word print and says, oh, just return nothing. And then we're left with the 42 sitting there going like, I don't know anything. All right, so let's extract a method first, because this is getting complicated. Print, I'll say print statement. And I'm kind of going top down on this file. I usually go either mostly top down or mostly bottom up. And bottom up is let's define a few lemmas, and then you can see the real business. And top down is like, here's what we're doing, and then read further if you want to figure it out more. All right, so that extract is a do nothing theoretically. I'm not going to worry about the file privates. And next token and print. Okay, well, at this point, I have parsed. I skipped over the word print. Okay, and now if it's if my next character or my next token is a number, because that's all I know how to do right now, then I want to put a value in. So in effect, this is kind of like our first one. Our program, we started off with an empty list of lines and then accumulated them. For us, I'll start that process. Okay, so var, let's see, I don't know, maybe values is array of parse, and it starts out empty. All right, and then I'm going to put that in here, values. Okay, so if my next token is a number, if dot number let's see, do I want to say it that way? Yeah, let's see. Let's say if number equals token, okay, then something's going to happen. Well, what's going to happen? We're going to get the value, and we've done that before up here. I thought we did. I guess I can do. Let's see. It's more like if let number sub. Oh, can I? Good Lord. Is it in here? I love these books online, but oh, I'd love a search. Okay. I would love if I had any memory left and I could do these. If let error equals error, now that checks for nil. If let enum or associated value. Oh yeah, it's case let now. Okay. That assigns this. Yeah. This is almost more readable to me. If case, whatever. It's not if case, it's, or if let, if case dot number let value equals token. Okay. Token has no member number. Ugh, why can't I remember how to do these? Sorry, this seems like the right thing. Switch token, case number, let data. That should be the way I can do it. Case let my value equals result. Token has no member number. Oh, it's integer. Oh. Talked about numbers so much, I lost myself. Okay, so now if case integer let value equals token, yeah, then we have a number there. We need to put it in a parse, so it goes in the number here. Okay. Let's say values.add, and then we need a parse, which is going to be a dot number. Are you going to know which one I'm talking about? Of value. Oh, maybe I don't even need that, do I? I need the token. Okay. Cannot infer values has no. How's this? Cannot convert number value type parse has no member add. Oh, it's append. Okay. Yep. Okay. So I can really do this more like diff.integer equals token. All right. So if case, choose. If case integer equals token. There's too many variations. Okay, so this is what you do if you have a enum with a attached value that you don't want to look at the value. You attempt to assign it with an if case, and if it is that value, then it is fine. All right. Now, for all that, okay, so we skip over the word print. We look and we see a token, but now we need to consume it. Okay. Otherwise, we leave our parser looking at the thing. So anytime we match a terminal, like an integer is a terminal, a token, then we have to consume it so that the next thing, we don't want to start parsing at 42 and look for a line number. Next, we want to start at the next line. All right. I think we're okay. Enough stumbling around for it, for sure. Let's check this. Okay, we're not okay. All right. Program line, token 25, yes. Basic parse print. Oh, we have print with nothing. Oh, did I not put values at the bottom here? No. Is my token not an integer? Let's step in and find out. Okay, so my result has just an empty print, which means it never came down this path, I guess. Okay. Let's debug that. Okay. Let's print token. At end. Am I not? Am I in the right test? Yes. Print statement with number. I'm in parse. Oh, let's see how, okay. Let's make sure. I'm gonna run it again. Do before and after. Print token. It's a print token. Okay, we'll step over. Now we did a next token, so print token at end. Okay. Let's run this one. Print token. Okay. This one we step over, it should be the end. Okay, and does it go? Well, okay, just do this. Okay, so that one works. This one doesn't. It doesn't see the 42 after that. All right, let's see what our tokenizer does. So I would have what I'm at this point. What I'm doing is I think my tokenizer, my next token, calls Lexer next. I'm feeling like, ooh, maybe there's something wrong in there. Okay, so here's the letters. We match, print, skip word, and return token.print. Now we've already squeezed out the spaces, so let's go skip word. I don't think that's an issue. It takes the word dot count, but let's break here and figure it out. Okay, so print value is print, good, and index is 7. 0, 1, 2, 3, 4, 5, 6, 7. Why is the index there? Oh, match while A to Z. Ooh, that's probably not correct. I mean, it shouldn't hurt to this, but it seems a little bit wrong. Okay, so it's trying to find the whole word, but it may not be a whole word. If value starts with rem, if value starts with print. Okay, so I guess we got to the end here. We're at the 4 and 42 at this point. Oh, yeah, I see what I've done wrong. Huh. Okay, so the match while skipped forward through all the letters. The rem then skipped another 7 and pushed us to the end. Okay. Wow. All right, let's stack this up a little bit. Well, let's take this and look at our Lexer tests. Lexer tests. Okay. So what we're showing is can I do something with multiple tokens? Yeah. Okay. Check token. I'm gonna do something like this. Oops. Okay. Well, that's enough. All right. So if I do this kind of thing, I'm gonna find print then number. Okay, so let's take this. All right, so token next, that should equal 25. Token lexer next, that should be token.print. And next should be integer 42. And then next should be add end. Okay, so I'm pretty convinced this function is going to fail. All right, let's run all these so it picks it up.
Let's go find Bunny Buns.
Continue. Okay.
Yeah, there's Grandpa.
All right. So the test. Whoop. Hey, buddy.
Let's go this way.
All right. Prints number. Okay, this test fails. Yeah, why does it fail? I'm at end. Okay. So I'm not equal to token. Right. So this match while it's I think so match while forces our way forward in the thing, but imagine like we have the let statement. You're going to say let x equals 3. We don't want to find letx. You know, we gotta match only the front end of that thing. Okay. Now I could. What would be the way to do this? Boy, I could back up. Yeah, see, what was misleading is rem really does want to just ignore everything to the end of the line, so it doesn't care. All right, but the other ones, they really want to only get the keyword. Okay, so let's let starting index equal index. Index. Let's put the space over the other side like a normal. All right, so let starting index equal index. Okay. Now I'm going to match while and get this value, but I'm going to restore my index. So this is kind of a look ahead going on here. I'm going to go forward, find the word, find the string of letters, and then I'm going to put myself back where I was. In rem, I ignore from the whole thing up till new line. This one, I'm only going to ignore. I'm going to skip forward on the print and leave myself in the right place, I believe. Okay, so let's comment this test. Oh, I did. Okay. Wait, what test failed then? Continue. Okay. Make only skip past the keyword, not past all the letters. Keywords in Lexer. And again, I'm kind of, it's like, that's more a message to a programmer. Okay. Let's take this off. Okay. Now, Parser Tests again. Let's take this off. And I expect this to work. But I expected it last time too, didn't I? Okay. So, let print take a single numeric value. now. That's the parser. We want to do the interpreter. Close that. Interpreter tests. Okay, so this one, we got the simple print. And then let's do a print with a value. Okay. It's going to look something like that, but fancier. 25, 35. Okay. Let's see. We'll apply that same process program with a line integer 35 parse print, and then this is like the value. Why does it not work here? I don't know. Okay, but the print takes values, and so number and then dot integer of 22. Okay, and what is your problem? Oh, I do that a lot. Okay. Reference to member program cannot be resolved. Why not? Like, why does the other one work? Okay, I'm just puzzled. I mean, what's the difference? Well, we know result is a parse. Maybe we don't know that here. Well, if I do parse dot, does it catch the others? Parse was never used. You know, that's okay. I guess I just need enough to force the type enough to know. Ugh. Okay. If you came back with a program, line 35, print 22 is what that boils down to. All right, and we interpret it. Okay, the output should be 22, I think. Okay, interpreter, parse, output, run. This should fail. Let's find our interpreter. Should be an empty string because that's all we print. Yep. Oh, new line. It just took it as a print statement, empty print statement. There's interpreter. Okay. So, print, yeah, all we do is print the output plus the new line. Output's the existing output, and new line's what we're adding. Okay. So let's do print. So function do, I can extract it, right? I had keystrokes for these things, and I just kind of lost it somewhere along the way. And I'm going to move that down. Okay. We usually take a break by now, actually by half an hour ago. So let's take a break. This should run the same way, one failure. So it'll be like 3 or 4 minutes. All right. All right, welcome back. Okay, so we just extracted this do print, just the existing stuff. All right, now notice our print method. We have we have stuff attached to it, but we didn't pull it out. Okay, so let's pull that out. This is let values, and we'll send values in with this. Okay, and values our parses, array of parse. Okay, so values is array of parse, and that's good. What have I done? Okay. Same status. Just passing values we don't use. Okay, but we need to use them now. Okay. Let's see. So we're just going to assume it's 0 or 1 items. Well, do we care? Maybe we don't. Okay. So the parse in this case is going to be numbers. Let's do I want to accumulate a result? Let's do that. Var result equals output. And result dot append new line. Oh, well, that's not even right. Well, let's do it like that. Yeah. It's right if you just have a print by itself, but if you have a value, I don't know. Maybe it is right, regardless. Okay. We'll return result. I really wish I had TCR kind of stuff going on here, but it should still fail. I'm not changing anything. I'm just refactoring the printing. Okay, now what I want to do is I want to go while there's in the values. Okay, so let's just do for value and values. We're going to do stuff, okay? And the values, we just made them parse numbers. Okay, and this is what I'm talking about, that we're not constraining these things very much, and maybe that's an issue. Hey. All right, so we've said their values. We said they are parses, and we know we're only sticking numbers in right now. I'm just not so sure. It's all right. Let's. It's like, how much do you want to enforce? All right, let's just assert it's in there. Okay. Let's say we got value. I don't know if I want to do that. I'm basically trying to say value is a number. So maybe I need that caselet, whatever obnoxious thing. If case value, dot number of let number token equals value. All right, so if our value is a number, let's peel out that token, and if case integer I'm running out of variables, sorry. Let I equals token. Okay, so if the expression is a number and the number is a integer and the integer has a value I, then we're going to append I. And let's put a space just to be okay. Yeah. Force the type to string. Okay. We need it. Oh, am I not right? Can it write into string? I thought that. Okay. All right. And then I think our belief is that this is what we'll really put out. Okay. That you always put a new line at the end of a print, and we're going to put spaces between. Actually, I'm not going to do that. No, I am. Okay. We'll let it go for now. All right. So we did support print with numeric value in interpreter. Now, why I keep stumbling around is like I'm leaving these obligations, all right? What happens if it's not a number? Well, it's probably, at this point, it's an error, an internal error, okay? If it's not an integer, it's an internal error. And, you know, if there are more than one values at this point, we haven't really dealt with it. So, okay. Let's go up to the top level. Where's Basie? Okay. Let's test this print. Now I'm kind of embedding assumptions in. Like, I think we're probably going to change that approach, but what do I know? Okay. So the difference is this one is the full-blown end-to-end. It takes the program and runs the interpreter on the program text, not just the tree structure. Okay. Whether the question is, what do I want to drive things with? And I think I want to drive them from those internal structures and then do an overall test on the outside. Okay. Oh, goodness. I should have grabbed a drink in my break. We're in the 90s today here. I don't know what that is in Celsius, but it's really hot. Almost body temperature. Let's see. Is that 42? So it's probably 40. Let's go back to our to-dos and see what we said we would do. Print with numbers. Okay, I would say we've done that. Well, yeah. Now I don't know if it's going to tell me the print. They gave a very vague description here. Print, we support comma, semicolon, and strings. Okay. And then the other thing going in my mind is like, maybe I do want more semantics here on this expression. Like maybe an expression should be a separate thing, and then we can print them. I mean, those are things that have values, and the statements don't. I'm kind of thinking my way forward on this. So expressions you're going to have 42, and you're going to have 1 plus 2, and other stuff. And the characteristic is that an expression, well, they're recursive. We want expressions to deal with expressions. I think maybe that's the next step. There is going to be some funniness because, like, how are we going to deal with this comma versus semicolon thing? What I'm thinking is that maybe a semicolon is a thing, an expression of some. A comma is an expression of some sort. That's kind of a a format expression. And it says whatever the output is, work your way to next column multiple of 10 or something like that. I think. I don't know quite. All right, but let's refactor this a bit and make the types a little tighter. Okay, so I'm going to say indirect enum. Okay. Now, I want this is an example. Maybe it's my only example at this point. Okay. So print, I'm saying, let's see, I want to do this without breaking the world if I can. Well, I'm going to do it and see what happens. Okay, so everybody who does this, how can I, okay, it should break a bunch of stuff. Let's see what happens when I compile. Can I convert parse to expression? Can I convert expression to parse? Values. Okay. So what I wonder if I can do, what if I made it also a parse? Now I'm saying it's another kind of parse. Is that allowed? Raw type cannot have cases with arguments. Declares raw type parse but does not conform. Yeah. Okay, that's not good. All right. Let's just deal with these. Okay, so the values for a print statement need to be expressions. It's okay, leave it on. Append parse.number. Let's do expression.number. That is fine. Okay, I guess I'm not buried in some list of impossible things. Values here needs to be expression. Running through values, case numbers is value. It's an expression. Yes, that should have to be true. Okay. And its token is an integer. That's true. Let's see if it all works. Yeah, so we introduce new expression tree. All right. That's a good thing. Okay. I don't know if there are other things gonna happen. print with expressions. Okay, so now I'm saying, oh, maybe we should do our expressions. Let's go back to our little one-page guide here. Operators, minus, plus, times, slash, up arrow, which is exponentiation, not and or, less than, greater than, not equal, greater, less than, equal, and equal. Now there's a funny little syntactic or grammatic thing. The equal here is comparison, but in the let statement, which can be implicit, you can make an assignment. So A equals B equals C means A equals true if B is equal to C and false otherwise. But the equals is sometimes the operator equals, and sometimes the assignment operator, and sometimes it's the comparison operator. Okay, and these are single character. There's 1, 4, 5, 6, 7, 8 single character ones. I don't know. Yeah. Okay, and then some these things, these pre-built functions. Always 3 letters, always 3 letters. This has a 4. This has a 5. Okay. Well, let's start simple. Plus. All right. Actually, I don't mind getting all the one character operators. Let's get those. Okay. So what my strategy is going to be is I'm going to define the tokenizer for the one character operators. These 5 and a couple others. Then I'm going to maybe do the others. Yeah, I'm going to do the multi-character ones. I don't know. I want to get the single character ones and get an expression working, and then I'll go back and do the multi-character ones. How's that? Okay, so let's do expressions with single character operators. Expressions with multi-character operators. All right. And then the other thing we have to worry about is precedence and associativity. So exponentiation, I believe, has the most. I'd have to check. I think usually it's right associative, but I'm not sure these old basics did it that way. Then next precedence is star and slash, and then minus and plus. Okay, so we'll start with plus, but let's get the tokens going first. All right, so now I'm back in Parser Tests. We got anything similar yet? I think we've done such simple stuff. Somewhere we have our integer. Okay, let's rename this. This is test integer. Because we don't, the fact is the line number is an integer, but its integerness is what counts for now. Okay. So basically we're saying check token, you give it something, and then you say what token do you expect. And let's see, do we have to say the word token in these? Again, I'm looking for ways to clean up my test code a little bit. The less characters, the fewer characters, the better. I suppose you could take that to a ridiculous degree, but I'm not concerned here. All right, let's run these. Okay. And we didn't do all the tests, but that's okay. All right. This is similar. We'll start with just one. All right. And this should be plus. Where's my tokens? All right. And I'm going to define, let's see. You almost have to do them one at a time because you end up with case statements and stuff that need it. Plus. Okay. This should fail. I hope it fails in a good way. Good. All right. Probably got an unknown error not yet implemented is not equal to token plus. Okay. And that's actually pretty close to right. Okay, so here's the numbers. Let's stick it in here. Case plus. Okay. We got these little helpers. I think we can just do index plus equals and be done with it though. Okay. Okay. I'm going to change this to single character operators. And again, I'm feeling the lack of parameterized tests. But let's carry on. Now, the other thing is, this code is very identical. Well, let's do it this way for now. We'll get the failure, and then it better fail the same way as the earlier one. Yep, error. Okay. Now case minus index plus equals 1, return dot minus. Okay. That sure looks similar, doesn't it? Oh, I didn't create one yet. Okay, what did I do wrong? Oh. Wait. Okay. Yeah, let's make it the right answer. Okay. Now, what I'm already feeling like there's duplication, right? I'm going to do this 5, 6, 7 more times or whatever. Let's bite the bullet and deal with the single character operators. So I'm going to define a little helper. Let single character operators equals, and it's going to be a map. And I'm just going to map these things. Okay. Plus goes to dot plus. Minus goes to dot minus. Okay. And let it be like that. Okay. So if I had that, I certainly could return single character operators sub Well, let's let answer, I say result equal this single character operators sub program subindex. I hope that's okay. Return result. Okay, let's try again. This is a map from character to token. Okay. Now, okay, I'm going to rename this. How about one char operators? It's a little simpler. All right, I can do case plus and minus. Okay. All right, now we'll take the bigger step. Check token star is going to be dot. I say star, because star might have multiple meanings somewhere. Check token slash dot. I think this is just divide in basic. Maybe I'll be consistent times. Check token. Less than. I have to go by prefixes. So let's do exponent. The problem with less than and greater than is, I don't know if it's less than, I don't know if it's going to be a less than, a not equal, or a less than or equal. If it's greater, I got the same problem with greater or equal. Equal by itself, it doesn't start anything else. So these, it's not getting as much as I thought I would. Okay. But anyway, I've got these four. Times, divide, exponent equals. Define them in token. And I'm going to start breaking these out a little bit. Okay. Case times, case divide, case exponent, case equals. And in my lexer, I need okay. This should fail 4 times. Yep. And let's put those character matches in. Exponent equals. Okay. I guess I can put those on one line. And this should pass. Okay, so you can see I mentioned yesterday about, tools that do this stuff. Well, this table is on the path to that. Okay. Okay. The other ones, they're well, you could imagine doing these as strings. That would be kind of interesting. I could do the less than, greater than, less than, equal before less than, and run through them sequentially. But this is okay. All right. So now I have these operators, but I don't have anything that knows what to do with them. Okay. So the parser, and this is where our grammar is growing. Okay. So our grammar right now, well, print is actually it prints with an optional expression. I guess I can do it like that. Okay. Again, I'm kind of blending grammar syntax and regular expressions. They're all kind of the same. Regular expressions don't allow non-terminals on the right-hand side. It's kind of what it comes down to. Or, well, they don't allow recursion. Maybe that's more accurate. Okay. But in any case, we got expression. And right now, we just have expression goes to integer. And remember, we changed the name from line to integer. Okay. So this is kind of our grammar right now. You print 0 or 1 expressions, and expression is an integer. Okay. We don't explicitly call out expression in our parser, though. Print statement, we just said number. Okay. We only allowed for the number case. But really, it's expression. Okay, so let's extract this to expression. And again, I'm going to pull this down. Ooh, values changes. I don't want that. Okay. Well, let's see. This. Okay. What can we do? Let's. I'm going to flip this around a little. I'm going to say value equals, let value equal this. And I'm going to move this down. Okay. I'm not sure I'm helping myself any. Okay. Now I'll extract this. Value expression number token, next token. Vector. Why no extract? Okay, we'll extract it anyway. Func expression returns a parse. Oh, it returns a parse or it returns a value? And value, I guess it's returning an expression. Okay. Let's take this much Okay, so my claim is I can say let value equal expression. Expression. Okay, this should all pass. Okay, let's check that in. Extract expression. Okay, so now we have expression goes to integer, and here's the thing, consuming that and returning that value. And it shifts that domain to expression now because we made our statements contain expressions, which is good. Expression needs a token. No, there won't be a token for it. There will be, usually these left-hand sides correspond to methods, so that's why the method is there. Thank you, though. The tokens aren't changing. We didn't change anything there. It really was a refactoring, yeah. But the right-hand side has the token, and we have to match it and then consume it here. But once you get through this, like, you have to make sure your grammar is not left recursive. So I don't want to do, expression goes to expression, blah, 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 because then my routine would be expression. First thing it does is call expression and, infinite loop or blow up my stack or whatever. But once you take care of the grammar, it's not hard to do this recursive descent programming where every grammar rule turns into a method or a function and returns the stuff. So the returning this part, if you parse, you don't have to have a parse tree. You could just parse it and match it, and you wouldn't have to return a value. But as you grow it into a compiler, you do. All right. So now we have expression. Well, we want to get fancier. Okay, so, and this is me kind of having enough experience with compilers and expressions to know I'm going to want a grammar rule that is factor. I mean, really, they go like, it's like, I think normally you do expression to term to factor, where expression gets your pluses, term gets your times and divides, and factor is just your value and parenthesized. Okay, so let's modify our grammar. Let's just go to factor directly for now, and factor goes to integer. Okay, and then I'm going to make it factor goes to integer, or factor can go to parenthesized expression. Okay, so here, just this little bit is how I get the recursive expressions, and eventually we'll get, plus and times and all that in there. But, this is doing the balancing of parentheses. So expression goes to factor. I could go to this one. It would go expression again to factor to expression with parens, and then to integer, and that would force my two left parens to balance my two right parens. Okay, so let's extract out factor. Okay, so expression, all it does is go to factor. So, I should be able to just extract it then. I don't know why I couldn't before. I had some sort of partial value or something going on. Okay, let's pull out factor and pull this down. Okay. All right, and this should all still pass. Expression goes to factor. Eventually we'll get terms and go there. And maybe I'm mixing a level. I may have to pause and look up some stuff. But all right, so expression, lowercase, yields an expression, which is kind of a parse tree, and it only knows factor, and factor is either an integer, is all we support now, but let's add parenthesized expressions. So parser, well, we don't have parens yet. Let's add those to the lexer. it's not exactly an operator, but let's add it. Case left parend, case right parend. Okay, and then our Lexer tests, I'm just going to add one for those. Left parend, right parend. Okay. And this test should fail. Because we didn't add these to our operator list. Good. Not yet implemented. Oh, I didn't put a case. Okay. Right. Alrighty. So let's deal with the parser. Okay. And I've been pushing, let's see, test parenthesized expression. For the most part, I've been coming in at the level of parse. When I'm doing these expressions, it's kind of easier to come in at a lower level. And I haven't worried about it. I haven't done it so far, but I think I would like to do this at just testing expression. Okay. It's a little bit grabbing in the middle for the test, but I think it's a better test when it's just that stuff. Okay, so it's kind of this test, but it'll be simpler in results. So we're going to do a double parenthesized expression like that. Okay, and parser with the Lexer, parser dot, and let's just do expression. Okay, and what do I want? I have to make this parse dot. Oh, I don't need a program. Okay. I would like this to be just the integer 21. I don't think the parens matter to me grammatically. Result is an expression. Protocol any is a type cannot conform to equatable. I don't know what the matter is there. Okay, let's. Result is parser.expression. Parser.expression returns an expression. Assert equal result. Let's make sure the type is right. Expression. Oh, this is not an array. It's just a single value. Okay, and I've got too much parens here. Integer. Let's just take out this stuff. Number 21. One more. Okay. If I have a parenthesized expression 21, I'm going to say parentheses are ignored. They make sure the tree gets formed in the right way, but I don't need them for anything that I know of. Let's see. So number integer 21. Okay. So now I'm calling expression. I return factor. And remember, I don't need to return if it's the only thing there. Okay. Factor is a number. Okay. But we want to do parenthesized now. So factor needs a new rule. It's got this second rule here. We don't support it. Okay. So let's say if the token is a left parenthesis, if it's a left parenthesis, what are we going to do? Well, and this is, if it's a number, we do this. So that's okay. Okay, whoops. If it's a left parenthesis, okay, we need to return somewhere. We're going to skip over the left parenthesis because we don't need it. We're not even going to track it. Okay. If the token is a left parenthesis, do next token, and then we're going to get the expression. Okay, because consume the left parenthesis, now match the expression. So we're going to let's let expression exper equal expression. Okay, so we're matching that part of the rule, and now we need a right parenthesis. Okay, so everything leaves the tokens in the right place, so we should be looking at a right parenthesis. Let's say if token equals dot right parend, we're going to consume it, next token. And then in the end, we need a value for our expression. Well, it's going to be exper. Okay, so we'll return that. Okay, so if we see a left parenthesis, we consume it. We call the expression to get the main body of it. We match the right parenthesis, and there's a little to-do here. What if it's not? And we return an expression. The expression is the one we parse there. Okay, and because of the recursion, you know, if it's any number of levels of parentheses, it's all going to work out. And I think that will pass. Parser tests. Okay, and so we've added support for parentheses. Okay. Now, the to-do is, what if it's not a right parenthesis? Okay. Basically, that's an error, right? If you just put 3 left parentheses, 21, and no right parentheses, or not enough right parentheses. Okay. If there's no right parenthesis, well, we're going to be back to our old throw and all that stuff. Okay. This is a missing right parenthesis. I don't know, parens, we say that all the time. It's just a shorthand. I think it's common enough I don't have to justify it too much. Okay. But notice the consequence here. We're back to this thing about throwing. Well, our expression could fail. Okay. If there's an error inside it, you know, which there are lots of ways to make an error. So this throws, and that's going to have impact all the way up and down, unfortunately. It means factor has to, well, we know factor has to be able to throw because it's the one that's going to do the throwing. Okay. And we have to do the try. And then this can throw, so it's got to be a try. Okay. All right. And then expression can throw, so whoever calls that has to do a try. And now the print statement might throw. Okay. And where's print statement? Well, statement already throws, but we need a try here. Okay. So we have to do all that bubbling up. Yeah. All right. And I haven't even made it support it yet. I've just put the mechanism in that will allow it. Oh, I have to do it here too. Oh, and I have to make this throws. I think that's okay. I don't know why the Swift parser is just a little bit behind things. It gets confused. All right, let's do the unbalanced case. Func test unbalanced parenthesis. Well, how about test missing right parentheses? And we'll do the same kind of thing. Okay, so let's just have one. Well, yeah, we'll do it this way. Really obviously unbalanced. Okay, try expression. Oh, this must be throws. Okay. Well, it's actually a catch. Oh, gosh, it's been a while since I did one of these. XC test. Check exception. XC test so it throws. That's the one we want. The class of the exception. I would have thought specific. NS exception. I think we give it the. No, there's another way to do this. I think I can, well, I probably could just do a do catch and do it that way, but well, they put the code here. I'm just going to do a do catch for now. Okay, I don't really need throws because I'm going to catch it. We'll just do it all in one big. Parse error dot missing right parenthesis. Okay. This, what's the matter here? It's not exhaustive. Okay. Let's do a fail here. Fail. Wrong exception thrown. This is okay. And if you get here without throwing, that's also a fail. Exception required, but not thrown. How about should have been? Okay. Got all that. I don't need the assert equal. Okay, so if this thing did not throw, we will catch it and fail. If it does throw, we want to make sure it throws the right thing. And if it doesn't throw the right thing, we want to get a message for that. Okay. We don't do anything, so this test should fail here. Or possibly, okay, exception should have been thrown. All right. That's the else here. Else. If we didn't see our right parenthesis, then we have to do a throw. Parse error dot missing. All right, let's intentionally throw the wrong thing just to check that. Make sure that third case, it should fail down here now. Yeah. Okay, so this should be missing. Right parend. Okay, if token is equal to right parend, otherwise, well, we want to, we're seeing a token we don't know what to do with. We've never attempted to parse on it, and we're back up at the statement level. So I'm okay. We don't need to consume anything. All right, now this should pass. All right, so error check for missing right parend. Yeah. Okay. I think expressions with single character operators. We haven't done that. I guess what we did was expressions with parentheses. Okay, and that is done. Expressions with single character operators. Okay, let's I almost want to go look up the grammar and make sure I get that right. I would have said I could do this in my sleep, and I probably could have a while back, but I want to be careful. All right, so we need, let's do 1 plus 2, okay? Let's move on. Okay, so expression goes to factor. Well, what I want to introduce is a term which is a factor. Factor, I think, should have multiplication. No, the term. Let's do it this way. Okay, I think expression, it can have factor and then plus or minus factor, and that can be repeated. Okay. All right. So we have our support for factor handles the parenthesized case, handles the number case. Okay. It's still not quite perfect, but that's okay. Let's get expression. So with expression, okay, so the question is 1 plus 2 plus 3. Is that 1 plus 2 plus 3? Or is it 1 plus... Now, I don't know what grade they teach you that, but, maybe 3rd, 4th, 5th grade, somewhere in there, right? Maybe 2nd grade, I don't know. But in addition, it doesn't matter, right? Addition is an associative thing, meaning either set of parentheses would work for it because of the value of the operator, but minus, divide might not be the same. I don't know. 1 divided by 2 divided by 3 versus 1 divided by 2 divided by 3. Okay. Maybe not the same. But from parsing point of view, like do we want one, line 50 or line 51? Well, for basic and addition, we want line 50. Okay. And so if we wanted 51, which would be right associative, we would have to we'd have to do some different work to take that into account. Okay. But from us, it's not so hard to match them this way. We just look and say, oh, I saw my 1. Now if I see a plus or a minus, do the rest of it. But if you want to return a value, you got to make sure you're returning something like this. Now, the parentheses here don't really matter because it's nodes. There's going to be a plus node with a 1 and a 2 in it. Okay. Okay, so we have our operators. We don't have a node that it can accommodate it. Okay, so today we just have numbers, but we want to allow for addition. Okay, so let's do add. Add, and it takes 2 expressions, the left and the right. Okay, and again, this is the recursion because building trees, trees and recursion fit together very naturally. Okay, so the tree for this, I can draw it the ugly way, but let's see, 1 plus, and then plus, and then 2 and 3. Okay, so the tree is something like that. Oh shoot. Well, I guess that was our choices, right? That corresponds to 51. We want plus 1, 2 plus 3. Okay, so at any rate, there's still trees either way, but we're trying for this one. We want 1 and 2 to form a little cluster, and then 3 to get added on to it. Okay, and that's going to correspond to an add for these pluses. So the first level, an add 1, 2, and then an add of that add and 3. Okay. 11:22. Well, we're getting late in the day for this. Let's see if we break things when we just add these options. 'Cause sometimes case statements require them. Okay, they don't in this case. Okay. Well, let's go ahead and add them all that we can accommodate at this time. Okay. Now I could put the token in there and have just one that's like operator. Again, it's just kind of trade-off number of these things versus what happens with them. I don't know. Maybe that would be better. If you knew you were a plus. Maybe so. Let's call it op2. Give it a token and an expression. And so the trade-off we're making is when we handle them, right, like our interpreter is going to look at op2 and it's going to have to decide, like, based on the token, do I do an addition, subtraction, exponentiation, whatever with these things, okay? If I broke them out separately, then I would have 6 or 7 or 8 cases, actually probably 15 when all is said and done, of these things. So I'm sort of pushing, like, is it the interpreter that's going to do the complexity, or is it the parser that's going to do the complexity? And it's not even that much complexity. So I'm going to go this way for now, and I may be wrong. And I'm just saying op2 because it's an operator that takes 2 arguments. Okay, we could have unary expressions. I think basic allows unary minus and maybe unary plus, depending on the basic. All right, so with this, that should all be okay if nobody's looking at these. And okay, I didn't know if our interpreter might, but apparently we don't do that yet. Okay, now op2, that can certainly accommodate the plus and so on. So what I'm going to have to do is my factor returns me an expression. If I see a plus, I'm going to have to capture that expression and then create a new node that's an op2. And then if it repeats, I'm going to have to get that value too. So it's a little tricky. Let's see. So what else do we need? The tokens, we've already got them. We've got the tree that can accommodate them. And let's look at our parser. Okay. I think maybe we can write the test. All right. So function test addition. I'll say simple addition. Let's start with the simplest thing we can do. Let's take this test. Okay. If we do 1 plus 2, and I could do 1 plus 1, but, I want to make sure I got the right order. I didn't swap anything or any of that kind of stuff. So that's fine. I'll make this a throws because I don't expect to need it. Okay, so if I run that, parse that program, what I get back should be an op2. So it should be an op2 with dot plus as my token and an integer 1 and an integer 2. I guess I need this brand number dot integer 2. That closes that. That closes that. Okay. This should fail. I mean, since we never used the word op2 anywhere except the one thing, then I'd be shocked if it didn't. I expect it comes back. I expect it's going to find the 1 and just return an integer node. It doesn't know to return the plus. Okay, so integer 1 is not equal to the big expression we came up with. Okay. Let me just make sure this should be nothing. Okay, I just want to make sure what we had changed. I think we just added the node. Okay. Add op2 node. in expression. So sometimes it's nice to start with a test all passing, and sometimes it's nice to start with a failing test so you know exactly where to start on the next thing. So we're going to follow the latter theory today. All right. So let's take a quick look at what we've done. And expressions with single character operators. Okay, that's what we're working on. All right, we did parens. Yes. Okay. So the trickiness in this, we're going to have to catch the expression, catch the result of the factor, and then have a while loop that looks for plus or minus to correspond to our grammar. Okay. And you can write grammars and not use these repeat operators. You can build them into the grammars, but I think it's fine to have them because the code, this star almost tells you like write a while loop, while plus or minus, if it starts with those two, then you can do it. Okay. So it won't take as long to do the next bit of expressions. All right. And the rest of the stuff, we did the rules around, let's see what review. We set up a better error handling approach. We did simple numbers. We turned those into expressions and made a separate type out of Parse for that, and did expressions with parentheses. And we started on these single character operators. All right. So next time I expect us to finish all the single character operators and probably the multi-character operators. We won't do the full expressions because there's still a bunch of, there are these functions. I guess we can get not and or. I expect that'll be pretty easy. Yeah, and that's good. Okay, so yeah, let's finish the operators. We maybe deal with floating point. Let's add that in just so we don't forget it. Okay. And then well, we don't do expressions yet. Okay, that's going to be easy. Maybe we do already. I don't know. Okay, that's a good place to stop, and we'll pick up tomorrow at the same time, which is 9 to 11:30 Central Time, or 10 a.m. to 12:30 Eastern Time, or 3:30 to 5:30 UTC. And thanks for joining today, and I hope I catch you in the future. Bye-bye.